Is
Okay.
that clear?
Yep, we see your screen.
Okay,
Okay.
let's start. Hi everyone, welcome to the section 3.3, and the first thing we should know is about the law of the cosines, which means that ABC is the length of side of a triangle, and suppose the side with length A subtends the angle alpha as the graph shows. We can get this formula that the A squared equal to the B squared plus C squared minus 2BC cosine alpha. And maybe you can be familiar with this Pythagorean theorem, which is when the alpha equal to the right angle, it means this part is zero, and the formula goes to the familiar part, which is A squared equal to the B squared plus the C squared. And let's go for the lemma 6.11. Let L be an L line in the P, which is the foundation for our mode of a hyperbolic plane, with the points
Sorry,
at
Haifeng. Is it okay if you just try to zoom in a little bit?
here.
Just to zoom in your screen, just to
Zoom.
make the thing bigger.
Okay. Is there okay?
Yeah, thank you. Yeah. Okay, sorry, go on.
With the point at infinity s and t, and let the torque equal to the absolute value of st. And if L is step 2 line, which is the interaction of a circle orthogonal to the circle C with the D plane, and let phi equal to the angle TXS, which is this one, for any x on the L, which is L line. And if L is a type 1 line, which means the intersection of diameters of circle with the plane, and we let the phi equal to the pi. And if x equal to the absolute value of xt, which is this part, and y equal to the absolute value of xs, which is here, then we can get this kind of formula. And for the proof part, if the L is a type 1 line, which is pretty simple, I think, cause the cosine phi equal to the -1, since the phi equal to the pi, and this part equal to the -x, and the sin square phi equal to 0, which means this part becomes a torque square. With the square root, we can become the y equal to -x plus torque. And to change the formula, we can get the y plus x equal to the torque, which show on this graph xs xt equal to the st, which is torque. And suppose S is a type 2 line. It's determined by the circle, and we can we can see the graph from here, which is familiar. We had show this part of formula, which is x squared. No, it's torque square equal to the b square plus c square, which is x, and y minus 2 yx cosine alpha, or cosine phi, sorry. And we can get this formula, which is we need to prove. So when we get this part by the quadratic formula, we can get the y equal to this formula, which I think is y equal to minus b plus minus square root b squared minus 4ac by 2, which is the simple square root formula, I think. And that's it. That's the formula how we get this one for the type 1 line and type 2 line. And here we come to the theorem 6.5. Maybe we get familiar with this on the Math 151 or Math 152. I can't remember when we get this, because it's years ago. It said let f be a continuous function from an interval I including into R to the R. If fa less than fb for some ab in the interval I, then for any y equal to the fa fb, there is an x between a and b, so that the fx equal to the y. And we put this on the graph, which means that on this axis, like we get a, get a b, which get value of FA and FB. It means we can draw a continuous curves without our pen leave the paper. Because we take any value during this interview, if this is not a continuous curve, then we can get the fx. We can get the x to the fx, which means y value. Because it's not continuous, so we can't get this value on this function. And from the lemma 6.16, we can see that let L be an L line in the hyperbolic plane with the points at infinity s and t, which we mentioned on the 6.11, and let torque equal to the st, which is also familiar on the previous one. If L is a type 2 line, let phi equal to the angle txs. And if L is type 1 line, that phi equal to the pi we mentioned on the 6.11. And we get this formula like gx equal to the x slash x cosine phi plus square root torque square minus x square and square phi. And we note that the g is differentiable on its domain with the continuous function. Because it's continuous function, so we can use differentiable, get this formula, and as the g slash for x bigger than 0, for all x equal to the 0 and torque, g is strictly increasing because this is bigger than 0. And on the calculus 1, I remember the theorem that we can see this is just increasing. And this shows that g is 1 to 1. And then let's notice that the limited x, when x equal to the 0, the g of x equal to the 0. Because that it's an increasing line. It's when it's x equal to the 0, like this part, we can see the whole part is equal to the 0 when x approaching to the 0. And that for the x approaching to the torque, for the gx, we can use the formula on the calculus 2, I think, for the differentiable formula. Since cosine phi less than 0 is here, and the square root of 1 minus square phi equal to the cosine phi, with the cosine square phi plus sine square phi equal to the 1. The formula we get on the Math 150. The denominator of cosine phi plus the square root arc square slash s square minus sine square phi of this part is approaching 0 from the above as x approaching torque from below. Thus, limited x approaching to the torque dx equal to the infinity. Hence, here we can set it's less than 0, and when x equal to the torque, we can see this part is approaching to the 0, and we can see okay, and that's for the 6.16, and here the last part is the theorem of 6.14. Let L be an L line in the hyperbolic plane we mentioned on the previous theorem. Let P be a fixed point on L. And the basic theorem of a fixed point, it means that a P on the point P and FP is on the line f or y equal to the P, which means FP equal to y. Or we can see P equal to the FP. It means it's just a straight line like y equal to the x, that line. And we suppose that S and T are the point at the infinity of L, which is also mentioned on the previous one. We let fx equal to the ln of ps, the absolute value of ps slash by the absolute value of pt, and slash with the absolute value xs xt. And then we can see f is a coordination of L by the r. And when we approve this part, we need to let everything be as hypothesized. We may view f as a computation of f equal to f1 commutation f2, where f2 is L approaching to the R plus by the f2x equal to this part, which is here, we can see. And also we can approaching the f1 with the R plus approaching to the R. It's the natural logarithmic function, and bijectively and continuously of L, which is L approaching to R, will follow if we show that f1 and f2 are both bijective and continuous. And for the continuous, we will see on the 6.12, which is works for here. And for the bijective is for the 1-to-1 mapping, like x, y, 1 to A, 2 to B, 3 to C, 1-to-1 mapping. And by our calculus course, we know that the natural logarithm, which is log x, is a bijective continuous mapping from R plus onto R. So we need only address the qualification of f2. Notice that f2 equal to the ps absolute value slash pt with the g mapping to the R, and where ps slash pt is a constant. And for here, I think it's because of it's a fixed point, so it would be a constant. And for the R, is L approaching to the 0 torque, which is torque equal to the absolute value of st, and the t and s is the points at the infinity. And it is mapping we discussed in lemon 6.10. We mentioned on last Friday. I think yes. And for the G, is from 0 torque to mapping to the R plus. It's the mapping from 6.6. We mentioned on the above one. And maybe someone get off with the 6.10. Let me just like a quick review. We can L be an L line in P, and TS be the points at infinite L. Let ST absolute value equal to torque. We define that L approaching to R by Rx equal to the xt absolute value. So if we will